I'm going to speak a little bit about pseudowires and L2TPv3 here. The goals of this talk this afternoon is to first define the term pseudowire and identify its relation to an L2 VPN. Secondly, is to show how the pseudowires can be used for network convergence. Third, identify where L2TP fits within the IETF PWE3 working group framework, and an overview of L2TP as a tunneling protocol for PWE3 over IP. And I'm actually going to get down a little bit into the protocol details, and leave more of the application space to Gilles, who has been using UTI, which is a precursor to L2TP in some of our Cisco products, as well as he's going to speak about L2TP going forward and how he's, some ideas that he has for using it. So assuming everyone's still awake after a little bit of protocol details, then we'll get into more of the application space. So first, a pseudo-wire. It's kind of a strange name. It's sort of like a wire, but not really. It emulates the essential attributes of a layer 2 service. So this is actually in the Pseudowire PWE3 framework document. Talks about this. But basically the idea is to take your frame relay, your PDP, your T1, your Ethernet, what have you, and create an emulated wire over your core network or whatever your packet switch network is. So the standardization is actually going on within the IETF PWE3. PWE3 is pseudo-wire edge-to-edge emulation, the three E's there, making the E3. So here's a picture. I'm going to talk a little bit about the layout, but again, leave the rest to Gilles. In this picture, you see a core IP network with your serial lines or two LANs, Ethernet LANs, or what have you, and the tunnels connecting them. You've probably seen this kind of thing before anytime you're talking about L2 VPNs. So essentially a collection of pseudowires together creates your L2 VPN. So one of the applications for pseudowire is network convergence, and there's a variety of types of network convergence today. So this is kind of a very simple one. I think I grabbed it out of some marketing slides somewhere. Basically, you have your parallel networks before, your IP backbone, and the frame relay backbone, if you can call it that. And I substituted in Miami here, but anyway, some global backbone, and you're maintaining both of them. The idea is after you go through the convergence, you still have your one global IP backbone, but you can still have frame relay connectivity outside the backbone at these different points of presence. So what this is really doing here is tunneling over IP. Now, one note here: PWE3 in the IETF actually covers any transport over MPLS as well, okay? And some of the draft Martini and stuff, which were the basis for this. So it's actually PWE3 is abstracted above the packet, the PSN, and the PSN, the packet switch network, can be IP or MPLS, okay? That's how the standardization effort is moving forward. In my talk today, I'm talking more about if your core network is IP, so there's no MPLS here, and L2TP being the tunneling protocol to provide the service to handle the layer 2 connections over your IP network. So 3 tunneling requirements to do PWE3 over IP. I've distilled down to here. There may be 1 or 2 more, but these are 3 important points. First, you need an efficient layer 2 tunneling and multiplexing encapsulation, because you're sending these layer 2 point-to-point connections all over your network. So the L2TPv3 encapsulation is actually quite simple. If you look right above your IP packet is just a simple 4-byte session identifier is the first thing you see. And this session identifier is designed to be optimized for the fastest lookup possible once your IP packet arrives at your edge node. In addition, there's an optional cookie field, and we'll talk a little bit more about what the cookie does. But it's another opaque field that is used for integrity checking to make sure that when the packet arrives and you do the session lookup, it really, 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 really is for that particular tunnel. And then you have your payload. And inside your payload is all your framing and so on and so forth. And this is different for every type of pseudowire, okay? So, and this is actually what's defined more in PWE3 is the stuff above the tunneling. And the L2TP provides the tunneling over IP for this. The second requirement for tunneling PWE3 over an IP network is easy tunnel setup, an easily extendable method for signaling pseudo-wire line events, state changes, etc. So at L2TP we have a control plane. Now L2TP in its simplest form is nothing more than the encapsulation that you saw a moment ago. But that's L2TP in its simplest form. L2TP also has a control plane that, as we see on the slides here, it's a simple in-band control plane for tunnel setup and maintenance. So if you want to set up your tunnels using this control plane, I'm going to actually go through the basic steps on how to do that. L2TP operates its own reliable datagram protocol that operates in-band over the pseudo-wire or between the PE routers. This is documented as part of RFC 2661. This is not new to L2TPv3. This is the same one that we've been using for years and years and years. It's also copied into, essentially, with some different wording and such, into the L2TP base draft. And there are some slight modifications, some of them that were simply a result of the interoperability experience that we've been gaining over time, and actually we're taking out of an L2TP BIS draft that we had that's now defunct. It's also designed to easily accept new messages and definitions for reliable delivery across this channel, and we've had numerous drafts that actually define this. So the setup phases for setting up an L2TP control connection or for a pseudo-wire for tunneling begins always with a control connection, what we call a control connection between two PE routers. This is three simple messages for starting as a request, a reply, and then a connected. So it's a three-way handshake that says, here, I want to be able to set up tunnels with you, and has a few features like optional authentication, which we'll talk about, and things like that. And you can also advertise, and by the way, I support these types of pseudo-wires. What do you support? So it's a simple three-way connection, and once that's established, you have the ability to send whatever messages you want reliable between those 2 points. A little bit like TCP here, but it's simpler, and it operates in band. So as I alluded to in the previous slide, the L2TP control connection includes this optional challenge handshake mutual peer authentication mechanism to establish identity. This is a very simple honest man's lock between the two edge points to make sure, yes, you are who you say you are. It's not IPsec. Once the control connection is established, multiple tunnels, which in L2TP we refer to tunnels as sessions, may be set up automatically as needed. You want to bring up 5, you want to bring up 10, you want to bring 1,000, you want to bring up 10,000. Okay, it's all. This is the steps that you go through just to automatically set those sessions up. Session establishment, similar to the control connection establishment, it's a very simple 3-message exchange: request, reply, connected. And in here, you can identify, I am the pseudo-wire type. Okay, I'm operating in this mode, or what have you. Once the tunnel is set up, you can maintain the tunnel, you can maintain line events. Now, in the simplest mode of operation, again, emulating the simplest types of pseudo-wires, you may not need any maintenance whatsoever in terms of line events and so on and so forth. An example is just an Ethernet or some such. But if you're trying to emulate a frame relay, and you want to it depends on how faithful you want to be to the layer 2 connection, and you want to signal your UNI and NNI events, then you need some control, some ability to send a message to your peer, and L2TP provides a reliable connection for that in a very simple way to just fire a message to the other side. And we use this in our PPP emulation with L2TP in the past for various line events. If you keep your state synchronized between the 2 points with these control messages, you have the luxury of having a single keep alive to cover all your sessions between 2 edge routers. So you have a single keep alive that says, yes, my state is the same on both sides. And by definition, it's the same on both sides because you've been signaling everything that's been happening on both sides. So this is just a side point. So maintenance includes not only a very simple keep alive between the points for dead peer detection and so on and so forth, but it's also ability to send a message for a line event. So TDM emulation, that actually is covered within PWE3, actually doing the timing and all that business, right? That actually operates above L2TP. L2TP is not involved in that. Finally, light and heavy-duty security options. The heavy-duty security choice is L2TP Security, RFC 3193. This is securing L2TP with IPsec. From the very beginning, we thought L2TP, when you really want security, use IPsec in transport mode underneath it. L2TP is still doing all the tunneling here. It's just IPsec is being used for the encryption or authentication or what have you. And this gives the operator to turn it on and off. Once you get your L2TP tunnel up and working, turn on your IPsec if you need it. If you don't need it, turn it off. And you've still got all the same tunneling features above. The light duty options are, one, the control connection authentication, the honest man's lock that says, yes, I am talking to who I think I'm talking to on the other end before I set up those sessions. And this is a shared secret simple password technique. In addition, we have the cookie field, which I talked about earlier. And this is a random 64-bit value that's stuffed inside each packet. Now it's the same for the life of the connection. You pick a random value, then you put it into every packet that's sent for that tunnel or for that session. So associated with each session to protect against a malicious blind attack. So we're going to talk about what exactly I mean by a malicious blind attack, or inadvertent insertion of data into the tunnel stream. And by inadvertent, I could mean a packet floating out on the network that happens to have the same session ID, and oops, it arrives later. You don't want to insert that into your customer's VPN. So to talk about the attack, a blind attack, the attacker has no ability to inspect data flowing on the target network at all. This focuses on a very small subset of a potential attack. Only the ability to insert spoofed data at will. So it also assumes that the session ID is predictable. So we have this 32-bit session ID that you would have to guess, but we want to keep that open to whatever indexed lookup methods or what have you for your particular hardware platform to optimize on. So if he wants to use just the first few bits for an index lookup, you can, and you don't have to worry about making sure that you're not picking something that you just, one index value that you just used last session and all that kind of mess. You can also set certain bits to go to certain line cards. You have the full flexibility of those 32 bits to optimize your switching or your lookup of your context info when that packet arrives. So so if you assume that session ID is predictable, then anybody could insert data whenever they wanted to. So this is why you have the cookie. So the 64-bit, the way it works, in order for the packet to not be dropped, the attacker would have to guess that 64-bit value. Now, why do we choose 64 bits? If you look back at the napkin calculation, you talk about brute force insertion, and that's what we're protecting against. And if you look at the goal to get one 40-byte spoofed packet inserted into a VPN at OC48 speed, 20 bits takes 130 milliseconds. 32 bits is under 10 minutes. But 64 bits takes 75,000 years. So that seems reasonable enough. OC192, all these values get divided by 4. And as you go on, they get divided by 4 again. So let's look close to that. There's some rounding error in there. So still you're at 18,000 years at 64 bits. So people ask me, what's new in L2TPv3, especially the people that are familiar with L2TP from the access and broadband world. The majority of the functionality is unchanged in 2661. The tunnel setup, the control channel, the maintenance, all this stuff is essentially unchanged. There are small modifications. There is a completely new encapsulation defined. This is a small part of the whole thing that is L2TP. This new encapsulation runs directly over IP. In 2661, we run over UDP. And this is still a valid mode of operation. And if you need the flexibility to run through NATs firewalls and so on, UDP mode is actually a bit more friendly to that, especially NAS. However, if you're running on a core network at the high speeds, you can run directly over IP. And then we resurrected the cookie field. The cookie field was actually something, we called it a key field, that we had 5 years ago when we started all of L2TP. It was a 32-bit value in addition to the session ID that's there now. But it was decided we decided to get rid of it. We figured, oh, we'll just randomize the session ID and that'll be good enough. But as we want to optimize the speed and push things down in the hardware, we decided, that was, Also, we heard some input from various individuals that said, hey, why don't you have a cookie field or a key field? And we were like, yeah, I remember that thing, and we resurrected it. In addition, in L2TPv3, something that's new is the separation. In 2661, we actually define L2TP and PPP tunneling all in one document, the single document there. And as we'll see in the little timeline here, people started using L2TP for things other than tunneling PPP. So this is more of a documentation exercise, an editorial exercise than anything else. We separated out the PPP part into its own draft and as a model for Ethernet and ATM and frame relay or what have you. So the timeline here it begins in August '96 with the first version of L2TP. The first version of the Internet Draft was published. We had a multi-vendor interoperability bake-off in 1997. The first version of L2TP over IPsec, I put that in there to show that from the beginning we've had a close relationship there in terms of what we wanted to use IPsec for in L2TP. And then in August '99, the RFC 2661 was published. So just to continue on the timeline, in June of 2000, Ethernet over L2TP Internet Draft was submitted. This is the first time someone publicly identified use of L2TP for something other than PPP. And so hence we came up with the first L2TPv3 and so on and so forth. And then finally in August 2001, the PWE3 working group met, and that was a culmination of any transport over MPLS as well as the work that was going on in L2TP to carry things other than PPP over Ethernet. So that's how the merging took place. So in summary, real quick, we've got to move on to Gilles. He's got about 10 minutes to talk. Pseudowires provide a network convergence by emulating a variety of data links, and L2TPv3 is based on a history of operational experience and standardization in the IETF. It's now being applied to PWE3 tunneling. And when you get these posted out on the net, there's a set of references as well. Thank you.
So this talk is about pseudo-wire services, experience from a service provider based on the first implementation called UTI and Cisco technology. I will first introduce the drivers for pseudo-wire services. One driver was a marketing driver, was to add a new service to the product portfolio that emulates circuit-like connection over a single or multiple IP networks, meaning over inter-AS, for point-to-point circuits or point-to-multipoint circuits. Another driver was more an internal driver, was to have a kind of performing and flexible toolbox to build customized solution in case we have some conflicting routing policy or peering policy. As a background information, Ebone network has different AS. We have regional AS and we have a transit AS. In those AS, the peering policy is different, so we have open versus restricted peering policy. A third driver was to interconnect at high speed physically disjoint networks by building a kind of overlay. And a last driver was to interconnect Ethernet networks transparently. Our requirements for UTI were at least the most important transparency. So we didn't want any change, to make any change to our routing architecture. We didn't want to implement a new IP protocol. It should run over plain IP, should be high speed capable from T1 up to OC48 or even OC192. Should be high performance, can be assisted by hardware for the encapsulation, de-encapsulation process. Should be flexible in terms of type of payload, so any type layer 2 payloads, PPPH, GLC, Family ATM or Internet. The provisioning should be easy and fast. We should have some security building. That was already introduced by Mark with the tunnel session ID or the cookie. It should be scalable, so we need a kind of mechanism for automatically or automatically set up the tunnels. The overhead should be minimum, so here in that case it's 4 to 12 bytes. And it takes benefit of the statistical multiplexing of the IP network. So let's go to the service part. The obvious first service is the IP virtual lease lines, where you create a kind of emulation of HGLC, PPP, Family ATM, Ethernet end-to-end. You transport the layer 2 packets end-to-end. It's a point-to-point service, so you have a single virtual lease line per physical interface. It's a one-to-one mapping where you bound one tunnel to a single interface. Here is an example where you have a tunnel between two post interface or two Ethernet segments. Examples are LAN-to-LAN interconnection. Another example is, for instance, a replacement of clear channel SDH. For instance, you have no trip cards available anymore for a particular speed, or your IDM is not capable, for instance, for VC44C, and the service would whatever be for router-to-router interconnection. Here, the big advantage is that you have a finer granularity in terms of bandwidth upgrades by using existing IP rate limiting tools. The last is a very interesting service that you can offer kind of a backhaul for a customer, for an ISP into a country, to another country, and build a kind of virtual presence at Internet Exchange. So there is no need for expensive lease line for that customer. A second stream of service is called that I call IP MVLL, so it's a point-to-multipoint service. So you have multiple virtual lease line per physical interface. How do you do that? Simply by creating subinterface on the physical interface with the help of the LCI VLANs ID 802.1Q or PPI VCI, and you bound each of these subinterfaces to the corresponding tunnel. What kind of service can you do with that? You can do layer 2 VPNs, provide a provision virtual private network, where you can have different topology, hub and spoke, partial or fully meshed. You need only a single interconnection per side. The customer manages his own routing and QoS, and the tunnels are provisioned by the provider. It can also be used as a kind of family VPN extension in the case you are not offering family services, or as a tool to migrate a family VPN to an IP VPN. We have used also UTI as a technology to build an overlay network. Typically here in the drawing, network D represents our transit network, network A and D represent regional networks, and network B represents the hosting centers. The hosting center should have all the peerings from all different networks. Networks A had an open peering policy, network D had the respective peering policy. So we achieve to have all the peerings in network B by building this pseudo-wire overlay. Another type of service is premium service, where you bundle different services on a single interface. An example typically is transit connectivity with multiple direct connectivity to a regional peering, or you build a layer 2 PPN VPN with internet breakouts and also kind of extension cords to manage hosting or hosting services. That's represented in that picture. can imagine also a metro transparent LAN service, and even break out this transparent LAN service to remote MANs. An interesting service is we have different AS, so per AS we need a router. So if we want to build a new service in new POP, we can use one device and just backhauling to the corresponding network for providing one of the service to the customer, like IP transit or interconnectivity to different regional networks. We can also offer a kind of premium service with different QoS requirements by building multiple tunnels. And the last quite interesting feature we have asked for is VLAN rewriting or stripping. So on the left-hand side, you have a kind of overlay network between switches. Instead of trying to keep some consistency end-to-end between the VLANs ID, you just rewrite at the end of the tunnel your VLAN, so you don't need to care about it. An example I've already talked about on the right-hand side is the internet breakout coupled with an interconnection directly to an internet exchange switch, where you are removing at the end the VLAN ID. So to finish, here are future requirements, like having a control plane for the forwarding plane, some more enhanced security, automatically tunnel setup, and also a layer 2 to layer 3 tunneling mechanism. Therefore, you don't need to have the same framing at both endpoints. I've also put on the slides 2 tips. One of the first tip is that the MTU at the endpoint interconnection should be lower than the maximum core MTU minus the 20 bytes of the IP header minus the 4 to 12 bytes of the tunnel header. That's because UTI doesn't support fragmentation. The last tip is that the IS hello message are padded to the maximum MTU size. So to avoid this, you can either disable it or you can set the correct MTU. Thank you. Any question?
My name is Andre from eBay. I have a question about the security of, I guess, not just L2TP, but network protocols in general. Something that has been addressed for a long time is covert channels. Every single, IP TCP protocol is vulnerable to some type of covert channel, like you have HTTP tunnel and mail tunnel and all those different programs out there. And even IPsec is vulnerable to a covert channel at this time. I just wondered, if anybody has any direction that they're moving towards for doing stuff to prevent covert channel attacks.
Are we there? Okay.
Yeah.
I'm not certain exactly what you're referring to when you say covert channel. If you, all that the light duty security options, or even the heavy duty security option, I guess this assumes that you know where your interfaces are and what they're connected to, and what your how your filters are set up. But I might be missing exactly what you're referring to and how it relates to this.
I guess it doesn't relate directly to it, but I think the security is just a misnomer with network security protocols, or network protocols in general, because any network protocol can bypass, especially tunnels, just make it even worse, because they're sitting behind the firewall, and it just allows a way in by just completely bypassing the firewall with the covert channel.
There may or may not even be firewalls in this particular
right.
Deployment.
I'm saying from a security perspective, when taking security into account.
Sure. Yeah, that's a valid concern, I would say. Covert channels are bad. Yeah.
All right, cool.
Thanks.
Hi, sorry. Tony Talbot, Genuity. The last slide had a point about control plane for the data plane. What was that about?
Oh. I think that was directed to
Yeah,
Gilles' last
Gilles, yeah,
slide.
Gilles' last slide.
That's referring to what's going on in L2TP version 3, so that you have a mechanism of building automatically the tunnels without having to configure it manually.
Oh, so like in-band control.
Yeah,
Oh, okay.
that's what I mean.
Thanks.
Okay.